Good evening, guys. Let us continue and try to complete the alcohols part today. If you remember, last session we discussed about um, O and H bond cleavage. O and H bond cleavage, and in that we majorly learned about esterification reactions. Got it? And if you try to recall, so these are a few examples of esterification reactions. We saw how the rate of the reaction changes, how the concentration changes will increase the rate, and intramolecular, or if you want to drive the reaction in the forward direction, what we need to do. These were some things which we learned. Now, today we'll focus mainly on carbon oxygen bond cleavage. Okay. In case if carbon oxygen bond cleavage is there, then what are the main reactions that you need to check? Correct. So let's see that. Suppose if you have alcohols and with some reagent you are able to get alkyl halide, which previously we learned in alkyl halides already. What are the reagents we used? PCl5, PCl3, SOCl2. These were the reagents which we used. Other than that, we could also make alcohols react with tosyl chloride and convert into this form, and Cl minus can attack, give you alkyl halide, and tosyl acid will be formation. So this kind of a product, this kind of a reaction can also happen where carbon oxygen bond is breaking. Next is dehydration reactions. Dehydration reactions we have learned in alkenes already that H and OH need to be removed using concentrated H2SO4, concentrated H3PO4, aluminium and aluminium oxide and heat, P4O10 and heat. Usually, if you use these acidic solutions, correct, it may be in the Lewis acid form or a dehydrating agent or completely a concentrated acidic solution, we will usually get alkenes by even mechanism. In case if you are reacting Al2O3 in the presence of pyridine and heat, then we would usually get E2 elimination giving a Shezhev product. But you want to get Hoffman product, then thorium dioxide is the reagent that we use. This will give you E2 and process via Hoffman product as the major. Got it? Next, if you want to do oxidation of alcohols, here more than bond cleavage, it is about carbon oxygen getting an extra bond here. So it is in proper oxidation case. So in this oxidation, if you notice the oxidation state of this carbon, it is -1. Okay. While if you notice in aldehyde, it is +1, right? It does make sense because there are two hydrogens here and one oxygen here. So it is like two gains and one loss. That makes it -1. And here it is like one hydrogen which is gaining towards carbon and two bonds which is losing towards oxygen. That makes it +1. And as you go towards the acid, it will become +3. Which means if you want to convert an alcohol into aldehyde, we expect to get two electrons, right? We have to release two electrons. So same way, from aldehyde to ketone also, aldehyde to acids also, two electrons are required. Okay. As our two electrons or two hydrogens are of same kind. Basically, what we are trying to do is remove this hydrogen here, which I'm highlighting, and the other hydrogen here at the alpha position. Removing these two hydrogens will make it dehydrogenation. So the reaction type is dehydrogenation. It is the dehydrogenation which causes the oxidation. Okay. Usually, if you have 1 degree alcohol, you will have a chance to dehydrate up to acids. If it is 2-degree alcohols, it can go all the way up to ketones, but further oxidation does not take place. Okay, and if you take 3-degree alcohols like R3COH that you are trying to oxidize, usually it will not get oxidized. This is the general oxidation nature of alcohols. Now, within this, the first of a kind we will see is Jones reagent. This will be used very frequently throughout the problem solving. So remember, Jones reagent. See, a chromic acid in aqueous acetone or H2CrO4, a chromic acid in acetone. But it should be sufficient amount of water should be present in here. Another way of representing this is CrO3 with dilute H2SO4 and acetone, or K2Cr2O7, H2SO4 and acetone together. Now, if you take this primary alcohol, so you can see this is a 1-degree alcohol that when you react with Jones reagent, first we will get aldehyde. Now, if you are using distillation, that is, as soon as the product is forming, you are trying to distillate this, then we can separate it. Otherwise, if the distill word is not used, which means you are continuing the oxidation and let it go all the way towards acids. So it will go all the way up to acids here. So 1-degree alcohol always gives acids with Jones reagent. Okay. Now, Jones reagent is a yellow-orange color solution. And after the reaction is completed, it will become bluish green. Check out the oxidation states also. Here it is at +6 oxidation state, changing to +3 oxidation state. While we already learned that carbon here was -1 oxidation state, changing to +3 oxidation state, which means from here to here, there are 4 electrons transfer. From here to here, there are 3 electrons transfer, which implies that for every 3 moles of alcohols RCH2OH, okay, 4 moles of acid is used. Sorry, 4 moles of H2CO3 is used. H2CrO4 is used. Please check this out quickly, everybody. Let's see how the mechanism is operated for Jones reagent. Okay. See, first, if you have an aldehyde here, alcohol here, that is CH2OH, and reacting with chromic acid, Cr double bond O, double bond O, OH. Now, what would happen here is dehydration is the first thing that you will expect, and that is causing ester formation. This is very similar to that of esterification. So I'll get this as R CH2O with Cr double bond OH. What we get here is chromate ester. So the first formation is about chromate ester. Now notice the structure of chromate ester, how it is. R, CH and one H here with oxygen, Cr double bond O with H plus have double bond O and OH. So the lone pair present on this oxygen will try to take the H plus from here, and water from the other end will try to extract H plus from here. This bond will be pushed and electrons will be pushed towards chromium, and this bond will be pushed towards oxygen. So this movement of electrons will cause, you know, uh, this chromate ester to convert into R, CH double bond O. Now this has become H2CrO3, chromous acid. So this will become chromous acid. So chromic acid will first convert into chromous acid. And keep noting out the oxidation states here, guys. This is +6 oxidation state. Now this has become +4 oxidation state. Okay, sorry, +4, +4 oxidation state. Okay, and then if you once get an aldehyde here, now notice along with the +6 oxidation state, even if the chromium is at +4 oxidation state, correct, that can also be used as a oxidizing source to convert into this radical form RCH2O dot, and Cr will convert into +3. Got it? And this radical which is forming RCH2O dot with chromium in +6 oxidation state, these two can interact to convert into aldehyde, plus chromium will convert into +5 oxidation state. And same way RCH2OH, when you treat that with chromium 5 oxidation state, that will be eventually converting into RCHO plus Cr plus 3 plus 2 moles of H plus. Correct. So this is how you can see eventually all the chromiums will convert into +3 oxidation states. So I hope you guys understood how it is happening. Now, one important aspect you need to learn here is that first, the oxidation will always happen up to aldehydes. Now, whether it has to go to acids or not, that depends upon how aldehydes behave. Like these aldehydes, as long as they are in acidic aqueous solution, and Jones reagent is in aqueous solution, so it would form something called hydrate, which means water will get added onto this double bond, it will become hydrate. This is called hydrate. And hydrate is the one which will again react with H2CrO4, again forms an ester, RCH, and we have OH here, this O forming a chromium here, double bond O, and double bond O, OH, H plus is present, same type of mechanism here. From here it will go, this bond will be pushed, chromium will go here, this way. And as that happens, now you will get this as RCOH double bond O plus this would become again H2CrO3. Done. So which means you would notice that eventually it will become acid, but it must have water along with it. Without aqueous solution, aldehydes cannot be converted into acids. Everybody understood? So this is the mechanism that you need to know from Jones reagent, everybody. So that's why I have written it here. If CrO3 is used in any anhydrous medium, like it is simply used in acetone but no water, then the final product you will report is only aldehydes. You will not report as acids. Second thing, whenever you have a double bond or a triple bond, they becomes unaffected if you are treating with Jones reagent. Which means, for example, if I take this reagent, what is the product I'll expect? The product I'll expect here, will be without disturbing the double bond, just oxidize this OH2 ketones. That is the product. There are many alternative reagents to convert alcohols to aldehydes or ketones. Let's see the first one. The second one, Saret's or Collins reagent. If you take CrO3, okay, CrO3 is a red color powder form. If you add it to pyridine, it would start making an acid-base reaction, exhibit like a salt. So this is dipyridine chromate. That is called Sarret's reagent. If Sarret's reagent is added to a solvent which is DCM, that is dichloromethane, then it is called as Collins reagent. Now, whether you take Sarret's reagent or whether you take Collins reagent, the role is the same. 1 degree alcohol will convert into convert into aldehydes. 2 degree alcohols will convert into ketones. Okay, and they are very selective. Okay, note, right? These are very selective, and does not disturb other functional groups. It does not disturb other functional groups. Next, very similar reagent, just like Sarret's and Collins, we have one more reagent known as PCC. This we'll be using quite frequently. PCC, pyridinium chlorochromate. Okay, what do we do here? Well, it is also called as Corey-Soups reagent, where we take CrO3 with pyridine, adding with some HCl. So when you do that, it is about pyridinium. First, it will become pyridinium chlorochromate because chlorine will get added on to this one. So it will become pyridinium chlorochromate in DCM. That will have same functions as that of Collins and Sarret's reagent. So understand this part, that all these reagents are in a way giving the same type of products. Next, if you have allyl 3 degree alcohol, if you take allyl or 3 degree alcohols, these will get oxidized by PCC as well as Jones reagent. Now, what does this mean? Generally, we learned that if you have any 3 degree alcohol, right, whether we take PCC or Jones reagent, you will not see any reaction happening. But in case if that 3 degree alcohol is at allylic position, then in such case the reaction will take place. Correct? Now how does it happen? See, first the lone pair from this OH will take H plus. That creates, you know, this double bond and making the positive charge here, because the water will go away, H2O will go out of it, and this positive charge will undergo, this will undergo rearrangement here. It's not rearrangement, resonance stabilization here. So we'll get positive charge here. And again, water as a nucleophile will attack on this position. So it will attack on this position. That makes it alcohol again. And now this has converted into 2 degree alcohol. Since it is now a 2 degree alcohol, if you push PCC or Jones reagent without disturbing the double bond, now they will convert into keto form. So this is how the allylic 3 degree alcohols can be oxidized, everybody. Okay. So I hope the role of PCC is clear, everyone. PCC is also used very similar to Sarret's and Collins. One very important case is 3 degree allylic. The next reagent we are using is PDC, pyridinium dichromate. Okay, so we have this dichromate with pyridinium ions attached to it. So this salt, when you add it to dimethyl dichloromethane, this is called as PDC and it functions exactly like PCC. So there is no difference as such. So this will also do the same job as what PCC does. Next one, you notice MnO2, another very important reagent. This MnO2 operates only for allylic and benzylic positions. So if you have an allylic alcohol or a benzylic alcohol, only those two positions will get oxidized. Like here, this is an allylic alcohol, converts into ketone. It is an allylic alcohol, 1 degree, benzylic alcohol, converts into aldehyde. So, if you have any allylic 1 degree, it will convert into aldehyde. Allylic 2 degree, convert into ketone. Allylic 3 degree, no reaction. Okay. So if you have non-allylic, let's say you have OH and double bond here, then you are treating with MnO2. In such case also, you will not find any reaction. So simple, MnO2 has a very simple role. It will only use at allylic and benzylic positions. No mechanism needed for these cases, so don't worry about those cases. Next, potassium permanganate, KMnO4. How does KMnO4 make reactions in this case? Let's see. So when you take KMnO4, you can take it in both acidic condition as well as basic condition. So KMnO4 in OH minus in basic medium, when you treat with 1 degree alcohols, so you can see this is 1 degree alcohol, then it will convert into acidic form or as carboxylate ion. Alright, and manganese will change into MnO2. So when it is in a basic medium, it is going to convert from +7 oxidation state all the way to +4 oxidation state. Got it? So 3 electrons are required for this reduction to happen. Okay, and here you know that from this -1 all the way to +3, you have total 4 electrons required. Correct? So 4 electrons will be released, 3 electrons will be accepted. So the ratio is 3:4. Got it? So you can see if you have a 2 degree alcohol, then the reaction would not usually, proceed after formation of ketones. Now, if it is 3 degree alcohol, that we have learned it already in the beginning of the chapter, that usually an alkane, 3 degree alkane, when you react with KMnO4 and OH minus, it will form a 3 degree alcohol, but further oxidation will not be proceeded. Okay, this we have learned it at the beginning of the chapter. While if you have any ketone, now listen up. If the ketone is unsymmetrical, okay, and moreover you are using some rigorous heating conditions, that means KMnO4 in basic medium is being heated strongly, then even ketones will break into bond formation and they all will convert into this type of acids. So there are 4 different acids we can expect. Now, the major product or a minor product depend upon something called a Popov's rule. Okay, this is called a Popov's rule. Let's understand what does that Popov's rule suggest. According to Popov's rule, the ketonic double bond O will always go with the smaller group. Okay, and that cleavage will take place in that particular direction of unsymmetrical ketones. Let me show you with some examples here. For instance, if you have the same thing, I have an alcohol here like this. Okay, now basically when you are heating it with KMnO4, OH minus and heat. Okay, more than Popov's rule, my suggestion is think about this way, that which direction you'll get more stable enol form. You know that this is a direction where there is more stable enol. So this is more stable enol. That's easy way to remember. And once you get this enol form, now you simply break the bond because double bonds are highly affected in the presence of KMnO4. So you can see this side we have 2 carbons that will convert into CH3, COOH, and the other side will also convert into CH3, COOH. So you will get only one molecule in this case, So this is the product that you will get. Okay, I mean, sorry, this is one molecule which is major. This is major product. In case if the double bond is forming on the other side, then this single carbon will convert into carbon dioxide. Okay, and the other carbon will be 3 carbon case, which is propanoic acid. So these two will be minor. Got it? So very simple case. Now notice how the Popov rule is applied. A smallest alkyl group should take C double bond O. Here there is ethyl, here there is methyl. So this is smallest carbon, so OH will go with that. Okay. So because that will get keto form here. Sorry, first let me write down ketone here. Write this as ketone. So this keto form will go along with the methyl group and not with the ethyl group. This is what we call it as Popov's rule. Clear? Now let me show you one more example here. Suppose if we have pH and then we have a ketonic group here and another group like this. So as you oxidize with it, there are two types of products you can get. Both sides they are sufficiently stable in all forms. This side also we have a stable in all form, and this side also we have a stable in all form here like this. Okay, in all form. So then you start bond breaking here and here. Notice as you start breaking the bond here, one will be PHCOOH, benzoic acid, and the other one will be, you can see 1, 2, 3, 4, 4 carbon, 1. So we have this as 4 carbons, 1, 2, 3, 4. Fourth carbon we have COOH. Okay, and next carbon to that we have methyl here. Sorry, I have 1, 2, 3, 4 carbon and adjacent carbon has this one has methyl here. Next, if you break it here, you'll get this as PH CH2COOH, correct? And on the other side, we again get a ketone, and this ketone will this will further get oxidized to give this as, same thing above. We get CH3COOH plus CO2 plus propanoic acid. So all these are products. 1, 2, 3, 4, 5, and 6. All these 6 are products here. So I suppose all of you got this point. So please check it out quickly. MnO2 and potassium permanganate, how does the oxidation works? Let's go ahead. The next reagent we need to look over is copper and heat or silver and heat. If we take 1 degree alcohol with copper or silver and heat, you will get aldehydes. 2 degree alcohols will give you ketones. 3 degree will give you dehydration and convert into alkenes. Okay. So reaction is simple. Oxidation is happening. Copper and silver will get oxidized. And copper and silver will help in oxidizing the alcohol into H2 gas. That will convert into this H2 gas here. Okay. That is a dehydrogenation step. While in the case of 3 degree, it will make it H2O, dehydration. Okay. So there's not much to discuss in this case. So the next reagent, 7. Now notice eighth one. Eighth one is CAN, can test also and can reaction also. So ammonium, ferric ammonium nitrate is called can test. So ferric ammonium nitrate is basically ammonium cerium nitrate, NO3 6. This is the complex. This complex is usually yellow color solution. What we do? We take an alcohol RCH2OH and react with this CAN. This will convert this into aldehydes. So it will convert into an aldehyde form. Okay. While converting into an aldehyde, so CAN changes color from yellow to red. So if there is a color change happening yellow to red, that means this is a uh, oxidation reaction. Got it? 1 second. Right. Please check. The same thing will happen even with the 2-degree alcohols also, RCHROH, and with CAN test here, so it will become aldehyde, sorry, ketone. So this will become R, double bond O, a keto will form. Again, color change will be yellow to red. Okay. Now, third one, if you have 3-degree alcohols, R3COH, 3-degree alcohols. 3-degree alcohols, when you react with the ferric ammonium nitrate here, this will form a complex. Okay, this will only form complex, and color is changing for sure. Not completely oxidized, but just the complex formation is observed. Okay, but what is an important note here is, okay, for 1-degree, 2-degree alcohols, okay, CAN will change color from yellow to red and then becomes colorless. After some time, it will become colorless, which means it is evidence that there is a 1-degree or 2-degree alcohol. For 3-degree alcohols, correct, CAN will change the color from yellow to red, but after it becomes red, it will not change into any color. So it will remain red. So if it remains red, that means it is 3-degree alcohols, correct? So if the question is given, is CAN test given for 1-degree, 2-degree or 3-degree alcohols? Answer is yes. You can predict 1-degree, 2-degree, 3-degree using CAN test. But only for 3-degree, the difference is it is not forming any product, but rather the color change is happening and color remains permanently. So it means remains red color only. Clear? Next. Check out ninth one. Ninth oxidation reaction is Swan's oxidation. Not very prominent in the syllabus. Okay, it's not usually asked much. Just I'll write down one reaction. That's all. So alcohol. When you react with 1-degree alcohol, when you react with COCl, COCl. This is how it is connected. So this is called oxalyl chloride. So oxalyl chloride, when you react that in the presence of DMSO or trimethylamine, then it will convert into an aldehyde form. This is called Swan's oxidation. Same way, if you have a 2-degree alcohol, with this Swan's oxidation, we will get a keto form. That's it. 3-degree alcohol, no reaction. 3-degree alcohol, if you try to oxidize, no reaction here. So this is Swan's oxidation. Like I said, not very prominently asked, but just to know that the name, if it rings somewhere, or the reagent if it comes somewhere, so just be aware of it. Next, X2 and water, that is halogen water. So this is again a simple case, mainly observed for 1-degree alcohols. If you have 1-degree alcohols, it will make a slow oxidation of alcohols to aldehyde. Okay, So this itself is a slow process where X is chlorine, bromine, iodine. Okay. And if it is for 2 degree CH, okay, with X2 and H2O, it is very slow process. So it might turn into ketone, but very slow process. So that's the reason why this X2 by water is mainly used for 1 degree alcohols. Okay. And the last thing is, if you have CH2OH and you're reacting that with NBS, N-bromosuccinamide, then also it will convert into aldehyde form. Okay. So I hope all of you got this. These are the 10 important reagents which are used as oxidation. In this entire organic chapter, okay, these are the most used reagents, guys. We'll keep on coming back to this in various questions. So please learn to know what are all these oxidizing reagents. Okay. Now let's get into the last topic of simple alcohols. That is about testing the alcohols. So test for alcohols. Okay. So I'll just quickly brief them. One is sodium metal test. So it gives a positive sodium metal test. Not much to discuss, I suppose. Okay. And second, it gives litmus. Litmus test is does not effective. Litmus test does not happen. That means no color change will take place here. Red to blue, blue to red, that kind of color change is not observed. Third test we usually conduct is ester test. Ester test. In fact, that means alcohols, when you react with some acid, it will give you fruity smelling vapors. So that is about ester test. Got it? The next is about can test. We just seen that can test. So can test is for 1 degree, 2 degree, 3 degree alcohols. So for all of them, it is positive. Fifth one. Fifth one. Achha, I'll do one thing. I'll just show you how the product is also here. See, suppose if you have an alcohol and if you react this with cerium nitrate this way, correct? So what happens here is this will become NH4 twice and cerium with OR group attaching here, and this will get NO3 5 times, and watch one HNO3 will come out, correct? So this is the one which is red colored. The same thing will happen with 1 degree, 2 degree and 3 degree. Okay, got it? I told you if it is 1 degree, color will disappear after some time, 1 degree or 2 degree. 3 degree, the color will remain. This is fourth one. Fifth one is basically test for phenols. So even phenols give brown color, brown color, coloration, brown coloration with can test. So it will also form a complex, but this time brown color is observed. Next, bromine water. See, bromine water is red in color, red color. Okay, and this when you react with 1 degree or 2 degree, 2 degree is slow, but yes, you can make it as a reaction. So it gets decolorized. 2 degree, this get decolorized. And alcohol 1 degree or 2 degree alcohols. So alcohols will convert into an aldehyde or ketone. This is sixth one. Seventh one is Lucas test. Lucas reagent test. We have come across that before, right? So Lucas test is mainly to distinguish 1 degree, 2 degree, 3 degree alcohols. To distinguish these three, we use Lucas test. Okay. If you recall it quickly, if it is 1 degree alcohol with concentrated HCl and ZnCl2 anhydrous, you're expecting this to be RCl formation, very slow, okay, very slow. So hardly you will observe any. So if it is 2 degree, and then you react with concentrated HCl and ZnCl2, it will convert into an aldehyde form. Let me put it as a 2 degree here. So if you have like this CH and R here with OH. So this will give you and alkyl halide form like this R and Cl, and this will be white turbid, and white turbid formation is observed from 2 to 5 minutes. Okay, and if it is something which is happening rapidly, that means it is of 3 degree alcohols or more stable carbocation. So in case if you have a 3 degree alcohol here like this OH, this is 3 degree. In that case, you will see white turbid forming instantly, rapidly or instantly. That's how you distinguish 1 degree, 2 degree and 3 degree uh, alcohols. Next, next. The next and last lab test. This is about lab test of identifying the type of alcohols is called as Victor Mayer test. Okay, let me call this. Let me write down that Victor Mayer test. This is used to distinguish. The test is mainly used to distinguish 1 degree, 2 degree, and 3 degree alcohols. Okay, see, this is how you need to check everybody. Suppose if I take 1 degree alcohol, okay, so there is a procedure that you need to follow. The procedure is you take red phosphorus, react with I2. Of course, it will go via SN2 mechanism to get RCH2I. Correct? Again, the minute you get iodide, you add AgNO2, AgNO3. Okay, sorry, AgNO2. As soon as you take that, AgI will get precipitated and nitrogen gets substituted again via SN2. So you get nitroalkane. When you get nitroalkane, you react with NaNO2 and HCl. This forms nitrous acid. Nitrous acid will react with this CH here and converts into NO and NO2. So you'll have this as NO and NO2. NO and NO2 undergoes tautomerism here, tautomerism, and convert into R, C, double bond N, OH, and the other one is NO2. This is what you will get. Okay. This form is called as nitrolic acid. This is called nitrolic acid. And nitrolic acid is usually blue in color. And this, if you react with NaOH, if you react with NaOH, then this compound will convert because it has an acidic hydrogen. It will give away this H plus, convert into O minus Na plus. And as it becomes this, it will convert into red color. This will convert into red color. Alright. Now let me do the same thing again till this point. But this time I'm taking the 2 degree alcohol. So imagine if at all I had 2 degree alcohol. So I had R here and this is 2 degree. So I had R here in all these cases. So I had R here, R here. So 2 degree. Up to this point, it is the same thing that will happen. Got it? Up to 2 degree, it will same thing that will happen. But since there is no hydrogen here, and instead we have only R here, so this is the product that you will get, and it cannot undergo further tautomerism because there is no hydrogen, no tautomerism. So since there is no tautomerism, if you react with NaOH, it will not respond to anything. So which means it will remain at which color? This will also appear blue color. So it will remain in blue color. It will remain in blue color. Got it? Now, in case if you have 3 degree alcohol, R, R and R with OH, 3 degree, reaction will take place, but these are all SN1 type now. So red phosphorus I2, I'll get R, C, R and R with iodide, and that when you react with AgNO2, up to this everything is going smooth, same reactions, you'll get NO2. But here onwards is the problem. So when you react with NaNO2 and HCl, now this is impossible to make any connection with this carbon. So furthermore, there is no reaction and this nitro is colorless. So this will remain colorless. Okay. So if you notice the same procedure, if you conduct for 1 degree, 2 degree and 3 degree alcohols, what you will get here is, for 1 degree alcohols, final color is uh, red. Okay. 2 degree alcohols, the final color is blue. 3 degree alcohols, the final color is colorless. This is colorless. Okay. So that's why you could remember it, like you can mug up or memorize this as RBC test. Just like how we write red blood cells. Here we are writing it as red, blue, colorless. So this is Victor Mayer test, everybody. This has been very important area for JEE mains. In JEE mains, Victor Mayer test will be usually asked because this is one of the um, um, tests which has been given in lab manuals. So from there, this question will be picked up. Finished? Right. Before going into further reactions, let me write down this eighth one here. One thing I forgot here is about iodoform test. Iodoform test. If you may recall, in case if you have an ethanol or any methyl secondary alcohols, these two gives positive test. Give positive test for iodoform. Okay. Examples: C2H5OH, any alcohol like this, as long as it is not tertiary. Alcohol like this, even if you have pH, OH like this. So these are all going to be positive iodoform tests, right? So guys, this is the first part of alcohols, where about simple alcohols with one OH group, which means only one hydroxy group. What are all the reactions that we have? Okay. So we got to, I'll leave this space in case if you, again, if we get any detailing or some important questions we come across, we can put it here. All right. So in that case, what we can do, we can get some extra detailing there. Now, let's get into the next part of the alcohols, which is about dihydrides or polyhydrides. So check out polyhydrides. That is more than one OH groups. Correct. In case if you have only two hydrides, that is called diols, and diols are generally called as glycols. So that too, when you have 1,2 or 1,2 or 1,3 or 1,4, then glycol word can be used. glycol is used. Okay, so that means suppose if you have OH and OH, the common name for this is ethylene glycol. Ethylene glycol. Okay, if you have like this OH and OH, so we call it as propane 1,3 glycol. Okay, so like this we can have different glycol forms. Preparation wise, and for our syllabus mainly we have 1,2-diol forms. 1,2-diol preparations. See, first from alkenes. From alkenes. We have already learned this. I'll just list it out here. Okay. We learned about Bayer's reagent. Bayer's reagent. If you recall, it is about KMnO4 OH minus in cold condition. So that will give you hydrate. Then we also have OSO4 in NaHCO3. Both in fact will give you, both are syn hydroxylation. Syn hydroxylation. Okay, next we can have MCPBA, peroxy acids followed by hydrolysis. Peroxy acid followed by hydrolysis, both acidic or basic. Acidic or basic hydrolysis, you will get the same product. Okay, next we can have O2 in Ag followed by hydrolysis. This is exactly same as that of MCPBA only. These are like MCPBA only. Next, if you have X2 in the presence of H2O, that too in alkaline hydrolysis, that is also from alkenes. Okay, or we can first make this as X2 in CCl4, then that is followed by alkaline hydrolysis. So these are all like a summary part. That's why I'm not writing it, because all of these reagents we have come across them already. The new ones which we need to learn is this one. Second, check out from aldehydes and ketones. Aldehydes and ketones, how we can get diols. Okay, so the first reaction includes CHO aldehyde. When you treat this with MgHg in the presence of H2O, magnesium, magnesium uh, magnesium amalgam in water, that would give us RCH connected with CH and R with OH and OH. This is how you will get the product. Okay, see the mechanism here. It's very simple mechanism. See, I have R, C, double bond O and H here. So because this has sufficient delta positive and delta negative charge here, so you will notice an electron will try to attack the carbon, and electron is coming from magnesium. So that will make it R, C, double bond OH with a dot. So imagine two times the same reaction is happening here with two different moles. Okay, so this is first mole, this is second mole. Now we will have these radicals, so these radicals will terminate. So 2 moles of R, C double bond OH, correct? Sorry, this will become O minus. After taking the electron, it will become O minus, O minus, O minus. So we will have this as O minus here of 2 moles with a radical. So those two will terminate with each other to give R, CH, CH and R with O minus and O minus. This is the kind of alkoxide which is formed. Okay. And now this alkoxide, when you react with water, it will become an alcohol part. That will become OH and OH here. OH and OH. So what is this one? This is pinacol. If you have any substituted diols, that is called as pinacols. Just me put it in bracket. Substituted diols. That is called pinacol. Clear? Second. Second reaction, let's see. This is from acylone. This is from acylone. Acylone by structure is like this: R, C, double bond O, CH. Already one alcohol is present and R here. So this, when you react with lithium aluminum hydride or sodium boron hydride, we know that they will reduce the aldehyde or a ketone into alcohol. So that's how you will get the diols here. That's how you'll get this as diols. So mainly these two are the reactions by which you can get the diol forms. Now let's see what are the chemical reactions. Chemical reactions of diols. The first one, reaction with PCl5, PCl3 or SOCl2. This we have already learned as a part of mechanism. So these are all repeats, so I'm not taking too much time onto it. So you have ethylene glycol. So it is like you react with SOCl2. You know that what is the product? You'll get this as CH2Cl, CH2Cl. So this is called vicinal dihalides. So you get to form vicinal dihalides and you'll get 2 moles of SO2 plus 2 moles of HCl. So that's how you will get the product formation. Got it? Second, if you react with CH2OH and glycol, in case if you are reacting that with Br2 in the presence of red phosphorus, then we will get this as CH2Br and CH2Br. Okay. Now here is a catch. Suppose if the same reaction is being done by iodide, suppose if you do the same reaction but this time with iodine, so that is if you take red phosphorus and I2, then you should get CH2I and CH2I. Well, you will just get this CH2I form here, but this uh, vicinal iodides are highly unstable. They're highly unstable. So that would immediately come out as I2. Probably the bulkiness, because of huge bulkiness which it carries, it will end up getting an ethene form. So this is what you will report. Okay. Third reaction. If we react with concentrated HI, okay, with red phosphorus in a very catalytic amount. Sometimes only concentrated HI is given. Sorry, not red phosphorus. We will first write concentrated HI. With concentrated HI, when you make a reaction here, see what do we get? So if you have a glycol here, OH and OH, and we react with HI, so first you will see iodide and iodide will come. And because iodides are unstable, you will get an alkene. And that alkene can further react with one more mole of HI and finally you will get this form. So you can see number of HI used. How many moles of HI are used here? 3 moles are used. Okay, this kind of database question will be asked, like how many moles of HI are used in this case. If we simply change it as concentrated HI plus red phosphorus, okay, plus red phosphorus, which means the reaction goes very similar up to this. Okay, it goes the same way from here to here, and from here even this iodide will get reduced. So with red phosphorus HI, you will just reduce this as well, and you will convert into an alkane form. So it will convert into an alkane form. Next, right? If you react with reaction with acids, correct? So for examples, if you have glycol and we react this with CH3COOH in the presence of H plus and heat, you know that this is esterification. So you'll get O, C double bond O CH3 and one ester above here and one ester below here. So this is the ester formation which you will get. Got it? And in case if this heat is been given, if heat is been given, so you notice that esters will perform elimination. So this O2 minus will go away, from here it will attach and this bond will go away here. Got it? So we will get something like CH2, sorry, not in this case, because bottom side we cannot see that CH3CO minus is ending. Here nothing would happen. But in case if you have, let's say, this case here, see OH and OH, and we have formic acid this time. So C double bond O, OH here, and C double bond O, OH here. Okay. So first thing, it will form a cyclic ester here, like this. Cyclic ester formation is observed. Double bond O, double bond O, cyclic ester is formed. And once it get a cyclic ester, now the bond breaking will take place. This will try to convert into CO2. This will convert into alkene. This will also convert into CO2. That's how you will get an alkene plus 2 moles of carbon dioxide. This is with oxalic acid. Okay. Next, sixth, with ZnCl2 anhydrous. ZnCl2 anhydrous. So it is a simple dehydration here, CH2OH and CH2OH. When you react with ZnCl2 and anhydrous form here, so make a dehydration, so we'll get CHOH, double bond CH2, CHOH and CH2. So this will undergo tautomerism and convert into CH3 C double bond OH, so which is acetaldehyde. Want to get acetaldehyde. Another reaction which you can notice is with concentrated H2SO4. With concentrated H2SO4, what do we get here is that CH2OH, I'll simply write it as glycol form, like this. This is the glycol form, OH and OH. And that when you react with concentrated H2SO4, it will get dehydration with 2 moles of it. So it will take 2 moles and get dehydration. This is read as 1,4-dioxane. Okay, numbering starts with oxygen. So that's why it is called 1,4-dioxane. Same thing if you are reacting that instead of 2 moles or n moles. If I take n moles and react with concentrated H3PO4 and heat. Okay, H2SO4 and heat is this, H3PO4 and heat. You will get a polymer form like this. Okay, so here you will get an oxygen extension like this. So N moles of extension. So you will get a polymer form. So it's called as polyethylene glycol. Polyethylene glycol. Or polyethylene glycol. Okay. So have a quick look of all the reactions, then we can. Whatever we have done is for glycols. Now the next type of polyhydrides are glycerols. Glycerols. Okay. Glycerol is another name for glycerine also. Glycerine. Okay. So how do you prepare that? See, preparation wise, it is CH2O, CHO, CH2O. This is connected to C double bond O, C17H35. C double bond O, C17H35, like this. Okay. Once again. C double bond O, C17H35. This is triglyceride. Triglyceride. So triglycerides, when you react with aqueous NaOH, right? If you react that with aqueous NaOH, see what will happen. So that would give away, this glycol form, which is CH2OH with CHOH and CH2OH, CH2OH, and we'll get 3 moles of C17H35 COO minus Na plus. This is the composition of soap known as sodium citrate. By the way, uh, sorry, sodium stearate. Sodium stearate. So this is the formation of the soap also. This is the same reaction that we use it for making of soaps as well. So this is typically how the glycol is being prepared. Next, check out the reactions here. Notice the chemical reactions. First one, if you have glycerol reacting with HI. So notice first you'll get I, and I. So how many moles used? 3 moles of HI are used. Next, we know that vicinal iodides are unstable. So I can make it one iodine here and a double bond here. And again when I add HI, correct? Again when I add HI, so this time I will get iodide here, iodide here. So you can notice one more mole of HI I have used. And this will also make 2 iodides to be unstable. Again an alkene is formed. One more HI can be used. So that will make it an iodide here. So how many moles have used in total? I've used one more mole here. So that makes a total of 5 moles. Okay. So 5 moles of HI can be used to convert this into final product as this one. Okay. What if I make a similar reaction? Let's make a very similar reaction here. Up to this same reaction, just the reagent change. The reagent which I'm changing is red phosphorus and I2. Red phosphorus and I2. After this, further on double bond, there is no substitution of iodine, so that will not take place. Got it? So this is where the product will stop. Next one, if you have, yeah, sorry, you got OH, OH, and OH here. And this, if you react with KHSO4 and heat, this on heating, this is a dehydrating agent. Since it's a dehydrating agent, first H2O will go away. So from the center it will go. So I'll get double bond OH, and this OH will remain. Okay. And because it is an enol form, you can see it will become an aldehyde form here like this with OH. Alright. That when you react with again KHSO4 and heat, alkene will come. Double bond O, double bond here, and H. So this is an aldehyde with unsaturation known as acrolein. So for acrolein formation, this is the reaction that is being used. So react with KHSO4 and you'll get acrolein. Clear everyone? So these are the reactions for glycerols. Of course, we can have more reactions for it, but more than this, there is nothing that can be asked in your syllabus. So this much would be enough. Now, the next important reaction, very important reaction in this area is something called pinacol, pinacol, pinacolone, pinacolone rearrangement. Pinacol, pinacolone rearrangement. See, what is pinacol? If you have OH and OH, this is called pinacol. Okay, what is pinacolone? If one of the methyl is shifted, okay, and I would make it like this: double bond O, and three methyl groups are present, and that is called pinacolone, pinacol and pinacolone. Okay. In case if you have any R groups like this is a pinacol. See the mechanism now. How does this pinacol converts into pinacolone? Basically, this reaction, if we react with any concentrated H2SO4 or concentrated H3PO4 or any good Lewis acid like BF3 or BF3 and heat, these are all with heat. So with heat, I'll write it at the bottom. So PCl5 or SOCl5, SOCl2 or TSCl, tosyl chloride. So you could imagine any one of these, correct, with heat. If you react, then the product what you will get here is R forming a ketonic group, and the other side we have R groups here, R, R, and R. Alright. So pinacol converting into pinacolone. So see the mechanism now. OH, OH, R, 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 and R is here with H plus. The lone pair present on oxygen will take H plus from here. R, 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 OH, OH2 plus. This is protonation step, first step. And from this, we will get an dehydration here. So water would come out of this. And now that OH2 has gone, so we will get a carbocation. Here is the interesting part. Once you get a carbocation, right? Once you get a carbocation, it would want to rearrange to get even more stable carbocation. And you know that nothing is more stable than octet completed carbocation, which means the lone pair present on oxygen, if at all it pushes. So positive charge coming at this position will be always most preferable. That's the reason why one of the R group will get migrated here. And as it gets migrated, you will have this as R with OH with plus charge here. The next carbon has three R groups here. This is how you'll get. And the lone pair present on oxygen will donate the electrons, and that's how you'll end up getting a double bond form here. Double bond O, H plus, and three R groups here like this. Okay, and you can see last thing, deprotonation will take place. The first step was protonation, now it is deprotonation. So due to deprotonation, that H plus and positive charge will go away, and finally you will get pinacolone. So starting with pinocol, converting into pinacolone. Got it? Let us do step by step. The first step is protonation. Second step is dehydration. Third step is migration. From here to here, migration happened. Correct? After migration, this resonance is not a step. This is just a resonating structures. Okay? These two are resonating structures. So we'll keep it like this. Then fourth step is the deprotonation. Okay? So pinacolone rearrangement for any case is this four steps only. So it will always happen through these four steps, starting from pinocol to all the way towards pinacolone. Got it? Now, of course, as you start having different alkyl groups, how many types of products you will get? Let's see. Suppose if you have this as R and R dash, this is R double dash and R triple dash, which means all four are different compounds, then what are the products you will get? Let me show you with an example. Okay. For example, if I take a pinocol like this, where we have all four different groups. One is methyl, ethyl, phenyl, okay, and let's say here we have propyl, okay. I'll take it this way, fine. So this, when you treat with H plus and heat, now watch steps carefully. Protonation could have happened in both directions here, correct? So which means OH2 plus could have formed here, or OH2 plus could have formed here. Okay, so from there we will get a carbocation. From there we will get one carbocation. That carbocation will be like this. We will have OH, PH, PR, ethyl, methyl with positive charge. And this side also we can get this carbocation. The carbocation this side will be PH, PR, positive charge, ethyl, methyl, and OH. Okay. Now, from here, the migration takes place, correct? So as it gets migrated, so see, what do we get? From here on migration, this positive charge will shift, and there are two products we can get. One, either the PR will shift and phenyl will be present here like this, and a double bond O will be formed. Directly I'm writing the product. This is with PH forming here. Or another product which I can get is with PR shifting here and pH here. So this will be PR and this will be pH. These are the two products we can get. Okay. While here, I'll just write it above. From here, if we write the products, again we can get two products here. We can get pH, PR with ethyl substitution with double bond O and methyl present here, or we can have the same thing, double bond O, ethyl here with pH, PR and ethyl. Okay, now notice one by one. This is a chiral center. After migration, this is a chiral center. So this will have two products. This is a chiral center. This will have two products. This is a chiral center. Again, two products. This is a chiral center. Again, two products. So including stereo, if you have four different alkyl groups on pinacoles, then we can get 8 different products. Okay, so I want all of you to please check once quickly. What is pinacole picocolone? Now see, what are the important pointers that we need to know it from pinacole picocolone reactions? See, these are some important noteworthy points. The first one being, okay, it's a four-step mechanism. It's a four-step mechanism. All good. Second, okay, reaction is, okay, intramolecular. Reaction is intramolecular rearrangement. Intramolecular rearrangement. Hence, no crossover products. No crossover products. No crossover products are formed. No crossover products are formed. What does that mean? Suppose if you have two different types of pinocoles I'm taking, let's say methyl, 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 OH and OH. This I mixed with another mixture where we have ethyl, ethyl, methyl, methyl, OH and OH. So these are two different pinocoles that when you react with concentrated H plus, you would not notice that this is ethyl and ethyl. You would not notice any kind of migration of this ethyl group to this side or this methyl group to this side. This type of crossover products are not observed. So which means what is the correct products we can get here? The product what we can get is double bond O with three methyl groups on it. This one plus the other product which you will get is ethyl groups on it. Ethyl, 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 double bond O and another ethyl. Okay. What is not formed is like this double bond O and some kind of a methyl, ethyl, and this methyl here. So this is not formed. This is a crossover product that is not formed. So this is a very important point to learn, that there is no crossover products that you will get. It is purely intramolecular. Second, next point. Okay. If there is a migrating the group which is migrating is actually chiral. If migrating group is chiral, migrating group is chiral, chiral, okay, then its configuration is written. Then its configuration is written. So that means while migrating, if it was R, then after migration also it will remain R. That is not going to change. Okay. So second, major product depends on depends on stability of first carbocation form. So whichever is more stable carbocation, that side you will have a product form. For example, I'll show you this also with example. Check. If you have methyl here, phenyl here, and only methyl and methyl here, and OH and OH. So definitely, if you react with H plus and heat, okay, the depending upon the uh, depending upon the stable carbocation, the protonation will first happen on this position. At this position, protonation will happen. So that if you push it further here, so what is the product you will get? So this OH2 will go away, and this is the positive charge which you will get. And thereafter, methyl will migrate from here to here. And after migration, you can have this as a product like this double bond O, methyl, phenyl, methyl, and methyl. This will be major product. That is what we have trying to understand that. So major product always depends upon which side you are getting the most stable carbocation to start with. Okay, next. Now, which while migrating, if there are two different groups, okay, in case of two different migrating groups, in case of two different groups for migration, two different groups for migration, then okay, migratory migratory aptitude decides decides the migration. Which one has to migrate depends upon its migrating aptitude. Okay. For example, any aryl group, that means phenyl lenso, is always most preferable than hydrogen, then 3 degree, then 2 degree, then 1 degree, then methyl. This is the migrating aptitude first. Second, within the benzenes, if you check out the migrating aptitude, correct? That means within the aryl groups, if you have to check out the migrating aptitude, which one has more migrating aptitude, then you just need to check out, whether they are donating or withdrawing. Like suppose we have OCH3, CH3, then we have chlorine, then we have uh, cyanide, and then we have NO2. Out of this, NO2 is most withdrawing, so therefore that will have the least migratory aptitude. Right? So which one will have more? So if I at all have this as 1, 2, 3, 4, 5, 6, then MA, which means migrating aptitude, will be most for donating group 2, then 3. Now, between chlorine, cyanide, NO2, and benzene, only benzene is better because chlorine and all, these are all withdrawing groups. So 4, 5, 6. So this will be the migrating aptitude. Okay. So these are very important pointers of pinnacle cases. Got it? Now let's see how the questions are framed here. So let me show you a few examples. First example. Suppose if you have a compound like this, a 5-membered ring with one OH here and one OH here. And this if you are reacting with H plus and heat. So because it is symmetrical on both ends, you can remove water from any direction. Let's say this is how the water has been removed out. Okay. So in that case, the carbocation will form here. So as soon as the carbocation is formed, you can clearly notice there is a chance of ring expansion. Bond will break from here, ring will expand. So as the ring expansion takes place, see the ring size now. So this will become a 6-membered ring from here. So this will remain 5-membered, but the connecting group will become 6-membered ring. And this carbon now will have OH with a positive charge converting into a double bond O. So this is the product that will report. Okay, right? Let me quickly add few more questions here. All right. So second, in case if you have OH here and OH here on this, then H plus and heat is being done. Then what is the product you will get? So first we will get a carbocation. I'm directly writing the carbocation. At this position, carbocation will be present. Now to get the positive charge on the OH group here, so bond will break from here and it will internally migrate here. So now what would happen here? One ring will become 5-membered ring like this, and the other one will become 7-membered ring like this. And adjacent to that, we will have double bond. So this is the product. Got it? So yes, there will be ring compression, ring expansion depending upon the need. Okay, because here there is a need because oxygen require that lone pair. Got it? Next, third, suppose you have a same structure here, but there is no bond between these two. Even then, because they are in a very similar situation like this, they're in a very similar situation this way, correct? With one OH2 going out here. Okay. Now in such case, the hydrogen present on it will migrate. This hydrogen will migrate. In fact, hydrogen migrating will actually reduce the strain also. So hence, you will get product like this with double bond O like this. That's it. That will be the final product. Okay. Fourth case, suppose I have one OH on this end, one OH on this end. Okay. So obviously getting a positive charge on the outward carbon would be beneficial because directly getting positive charge on the ring is unstable. So first you will get a positive charge here by removing that outward alcohol form, and then the ring expansion will take place. Bond will go here and you will get a 6-membered ring with an double bond O. So this is the product you will get. Got it? So I hope all of you are following that. Okay. Similarly, if you have on a similar situation, I'm writing, I have phenyl here, OH here, and OH here. In that case, if you are reacting with H plus and heat, we will get very similar condition here also. will get positive charge here with OH. Again, the ring expansion takes place. You will get a six-membered ring with two methyl groups, two phenyl groups here, and double bond O at this position. Okay. Now these are semi-pinacolone pinocole cases, which means instead of directly having two OH group, it might be one OH, one chlorine, pH, methyl, ethyl, methyl. Let's say this example. And instead of using concentrated H2SO4, we can use AgNO3. And using with AgNO3, you know that AgNO3 will make a precipitate with Cl, forming an AgCl precipitate. So if it forms AgCl precipitate, same pinocole-pinacolone situation will happen. And between methyl and ethyl, we know that ethyl will migrate. Migrating attribute of ethyl is more than that methyl. So we will get this as methyl with double bond O, and this side we have phenyl, methyl, and ethyl. So this is the product you will report. This is semi-pinacolone cases. Got it. So similar case, suppose if at all I take a similar case here, got it, where instead of chlorine, now I have NH2. If you have NH2 and then I use NaNO2 and HCl, NaNO2 and HCl will make a diazonium salt. So here this will become N2 plus, N2 plus, and N2 plus is highly unstable. We learned this already. This last week we learned this, that diazonium salt formation. And since it is highly unstable, it will form this carbocation here and releases N2 gas. And now again, who will migrate? Ethyl will migrate, and finally you will get the same product. Okay, you get double bond O with phenyl, methyl, ethyl, and methyl. Okay, so this is semi-pinacolone cases, semi-pinocole or semi-pinacolone cases. Got it? In fact, there are many cases as of now. These many cases are sufficient enough. Got it? Okay, this last one case I'll give you. So instead of directly having an what do you say, diol, it might also happen to have this epoxides also. So when you have this epoxide, that when you react with concentrated H plus, then first protonation will take place. So we will get this as H plus here. Got it? Now bond will break onto one side here like this. Okay, carbocation will form. Here carbocation will form on this end here like this, OH, correct? And that will have methyl and methyl positive charge. Now it can break the ring on this end and expand the ring. So that's how you can get a 7-membered ring this time with methyl and double bond O. So this is a product formation. Clear, everyone? So I hope all of you understood this logic. So these are few cases. We have a lot more cases in assignment also. So you guys can actually go through them. But yeah, more or less, this is how much you have it for alcohols topic, everybody.